Good morning, Math 105. It is good to see you again. So we have really only 2 weeks of class left this semester. So there's just a couple more topics that we're going to talk about together. The first one that we're going to tackle today is we're going to take a closer look at probabilities and ways of sampling. As we were talking about in our last live stream, what probability and statistics are really about is about learning something about a large population or a big question by studying the properties of a small subset of that population called a sample. And so how that sample is selected from out of the population has a big impact on the kinds of conclusions and the quality of the inferences that we can make based on that small sample. So we're going to look today at some different methods for sampling and what are some of the ways in which statistics, if not conducted in the right fashion, can actually be used to misinform people rather than to inform people. The stuff we're going to talk about today is really sort of key to making sure you're an informed consumer of statistical information that's presented to you in the media, in the workplace, in politics, really anywhere that statistics are used. There's a potential that they are misused or used in ways that might not support the conclusions that are trying to be drawn. And people are very savvy about how to use statistics in just the right, slightly colored way to give you an impression that the data, the underlying statistics and the analysis, might not actually support. So that's the main goal of what we're going to talk about today from the perspective of the mathematics that we're working on. As we move forward into next week is going to be our last live stream for the semester. We're going to talk about distributions, statistical distributions, in particular the bell curve, so-called bell curve, the normal distribution will be the topic of next week. And for these last couple of weeks, what I'm going to do for those students who are taking my course this semester is I'm actually going to combine the quizzes together to do 2 learning standards at a time. So the next quiz that will be posted later on today will cover learning standards 9 and 10, so both of the things we're talking about today, probability, arithmetic, and also sampling. And then the final quiz for the semester will cover standards 11 and 12, which are both about statistical distributions and probabilities, including the normal distribution, the bell curve. So that's how we're going to round out the semester, and then we'll have a final exam will be available in another week or two for you to work on. And be watching, if you're my student currently, be watching Slack for announcements about due dates as things evolve over the course of the next couple of weeks. So real quickly, the first thing I actually want to do is to take just a moment, and I guess I didn't put this on the agenda. Let me make sure it gets to the agenda here, is I want to talk about what are the next steps in our semester project that we're working on. So last live stream, I introduced the project for the semester. This is the so-called House Hunters project. And in that introduction, let me actually switch over to browser real quick here. In that introduction, I sort of talked about the goals of this project being that you are able to take some information coming to you from a real life context of a situation that you may already have experienced in your life. I have once, and that is buying a house, figuring out whether the house that you have in mind is one that you can afford based on what you know about your income and your assets and all of that wonderful stuff. And being able to balance those two pieces of quantitative information. On the one hand, there's how much will this house cost? On the other hand, how much money am I making to be able to afford the payments on a mortgage for this house? So hopefully by now your group has selected a House Hunters episode to watch, and you've learned a lot of information about the buyers and the house. Right. So about the buyers, we want to know what is their typical, what is their job? What are the jobs basically? And about the house, we want to find out as much as we can about the location and the parameters. So where is this house? After all, location is one of the biggest factors in how much a real estate property costs, but also what are some of the other parameters about it? How many square feet, how many bedrooms, how many bathrooms, just the basic stuff that a real estate agent or a buyer would want to know about the houses. So the next steps on this project are going to be to get more specific about the buyers and the house as far as the values of these things. So step 2 for the buyers is to figure out between the two of them, if it is a couple that you're looking at in your episode, what do you expect their annual income is going to look like? How much money before taxes, so gross income, do we think that they're going to be making in their jobs per year? So to figure this out, it's an opportunity to do a little bit of research. There are a lot of different sites online that you could go to research how much money people in certain careers make in certain places of the country. But from the point of view of information literacy, probably one of the more authoritative sources that we can go to is the federal government's Bureau of Labor Statistics. So the BLS maintains a public database of wages. And they keep this updated, I think, on a more or less annual basis. So when you pop this up, it's May of 2018. And so from this, you should be able to drill down into various categories of careers or jobs and figure out what are the sort of the typical wages that somebody makes in those careers. So let's, for a moment, just take a career just as an example. Let's take my career, which is math professor, higher education. Right? So if I'm looking for my career in this database, I would probably first want to go down to education, training, and libraries. I'll drill down into here. I'd look for math teachers. So let's see, mathematical science teachers, post-secondary. That would describe my job, so I'd drill down into here. And on this screen, I would find quite a good amount of information about the typical wages for somebody in my position. And this is on a nationwide basis, national estimates. So we can see, for example, here is the median wages for a post-secondary mathematical science teacher. Median, of course, means that half of people that are in this career are going to make more than that amount of money. The other half of the people in this career are making less than that amount of money. So if you are able to get these statistics, the percentiles, the 10th, 25th, 50th, 75th, and 90th percentiles for the careers that your buyers have, add them together, you'll figure out, on a roughly speaking at least, what on average do we think that these buyers are going to be making per year in an annual, on an annual basis, before taxes, gross income. So if you do that without choosing a geographic region, what you get is a nationwide average. So the process that I just went through gives me the nationwide average across the whole U.S. Half of mathematical science teachers at the post-secondary level are making more than $73,230. The other half are making less than $73,230. But, of course, we want to be as accurate as possible in considering the circumstances of the buyers and the house and everything that you're looking at in your project. So let's see if we can get a little bit more geographically sensitive data. Rather than looking at the nationwide average, I instead want to start by selecting a metropolitan area. So in the introductory video that I shared for a teaser for this project, these two buyers are buying in Beverly Hills. And of course, Beverly Hills is one of the richest zip codes in the country. It's certainly one of the richest in the Los Angeles area. So I'm at least going to start by selecting in California for those buyers. I would select the Los Angeles area. Los Angeles, Long Beach, Anaheim. I'm just going to choose that. And if I choose that first, and then I drill down into my education, mathematical science teachers, post-secondary, that's interesting. So it looks like, hold on, I think I did one too many clicks here. Go back a step. So if I go down into education, training, and library, what I get, it looks like it doesn't have the geographical data for this. It just gives me a footnote. So in this case, I'm probably going to choose the closest thing that I can get to that wage. Maybe I'll choose computer science instead. And notice that the numbers here end up being a little bit different. So do the best you can in your project at either getting a national estimate if you can't get a geographically sensitive one, or if you can, get the geographically sensitive estimate for what is the average or the median, whichever one you can get out of this BLS website. What do you think your buyers are going to be making per year on an annual basis? And that's going to be one of the most important things to know about them. For the sake of this project, at least for your initial analysis, we're not going to take into account any other assets that they might have, investments, savings, things that they could sell or pawn or do anything to be able to afford a down payment or be able to afford their mortgage. You're going to make your decision just based on their estimated annual incomes. So that's the thing to learn about your buyers during this week of the project. Then there's something to learn about the house itself. So the House Hunters TV show will usually provide, as part of the show itself, an estimate for what the cost of, what the actual selling price of the house is that they're looking at. But I want us to fact check them. Right? I want to know whether the figure that they provide in the show is actually realistic for a similar property located in a similar location of the country. So to figure that out, learn as much as you can, as you did last week, about the house that was bought on the show. And then use a home value index database. So this is not, there are more or less authoritative sources on these. Probably the most authoritative would be the MLS, the system that the realtors use to actually list and value properties. But that's really sort of cumbersome to navigate. So for the purposes of our project, I'm okay if you use Zillow. Zillow is a commercial online sort of real estate marketplace where it lists a whole bunch of houses and different kinds of properties for sale. It tells you all about them, it gives you pictures, and also gives you an estimated selling price. And they maintain some historical indices of home prices over time that allow you, for example, if I go into this data, to be able to look for, and what is it I'm going to look for here? I want the, I actually want two different data sets. I want the median home value per square foot by city. So again, this is going to let you choose the closest city to the house that your buyers are purchasing, and figure out, based just on square footage, what do we think the value of this house is going to be. So if I did that, try and find, where is it? I want median home value per square foot. Sorry, my head's in the way here. So I actually want median home value per square foot as my data type right here. And for geography, I'm just going to choose, again, the closest metropolitan area that I can get to where the buyers are buying. Since they were buying in Beverly Hills, I'm just going to choose zip code because anyone who watched TV in the 1990s will know an example zip code for Beverly Hills. That would be 90210. So what happens when I click download is it downloads for me a spreadsheet, an Excel file. And let me open up that Excel file here, just so I can show you around a little bit at what kinds of data is coming out of this really sort of large Zillow database. Just give me a moment here. I'll bring the Excel up onto the screen. Having some issues getting Excel to show up in our stream here. Not quite sure why. Let's see. I'll just slide this over here. Got to do a little bit of troubleshooting. Close Excel and open it back up one more time because I'm just having some issues getting it to display. My apologies. So open this up. And somehow it still looks like it doesn't want to work for me. Let me try just changing one more setting here before I try a different approach. I'll try a different approach here. All kinds of technical difficulties today. All right, we're going to try this one different way. Not going to be able to get. All right, so here's how I'm going to do this. I'm actually going to real quickly make a couple of tweaks. So I'm just going to put this data, I'm going to upload it into Google Drive. This may be something that you want to do as you're working with your teams so that you have a spreadsheet that you can all share. So I'll just show you how to do that here, because it's also going to be a workaround for me to actually get this to display correctly in my stream today. So I'm just going to log into my Google account. And let me get back into the browser. All right, so here's how I'm going to do this. I downloaded my Excel file. I'm going to upload it into my Google Drive. So here it is, mean value per square foot, all homes. That's the file that I downloaded off of the Zillow research site. And then once that upload is complete, when I locate that file in my Google Drive, I can right-click and choose to open it with Google Sheets instead of trying to open it as an Excel file. What that'll do is it'll convert that Excel file into a Google spreadsheet. Now we'll be able to actually see what's in this sheet, and I'm again going to help you to make sense of what's here. Ultimately, why we're doing this, remember, for the project, is we're trying to get a better sense of how much is the house that your buyers are buying on the show actually worth, given that it's located in a certain zip code. So for the purposes of today's demonstration, that zip code is going to be the Beverly Hills zip code 90210. So as soon as as soon as Google Sheets is done converting this thing, what we can do is look for the zip code that we're looking for. And what you'll notice, first of all, is that the Zillow site organizes the data in a way that is maybe not optimal for what we're looking for. It organizes it by size. So the very largest zip code, the most populous in the country, is the 10025 in New York. Second largest is Chicago, 60657, and so forth. So what we want to do is we want to find just the Beverly Hills zip code that we're looking for. So to do that quickly, in Excel or in Google, we can create a filter. I'm just going to click on the little filter button to create a filter view for my database. And because this is such a big database, Google's being a little bit slow in getting this all set up. So maybe rather than waiting, I'm going to do this the quick and dirty way, which is just to do a search. Search the spreadsheet. Oh boy. And I can search the spreadsheet. Oh, I guess the filter's working now. All right, so this is still going to be a little bit slow. Sorry, my apologies. Here we go. So this is going to be still a little bit slow, but what I can do then, once the filter is created, is I can click on this zip code drop-down over here, region name, and I can just type in the one that I want, 90210. So I want to clear all the other ones, and I just want to select the one that I want. And again, it's probably going to be a little bit slow. Clear all my values and select only the one I want. There we go. And so now that I've done that, now I have just the data right here, right on the median. So again, we'll look back on Zillow and figure out what this data set actually is telling me. Get back to my Zillow site. So this is telling me the median home value per square foot. Right? So how I can understand these numbers, I'm going to scroll over to the right here and look just at our current year. So the current quarter in the current year. So this is the third quarter of 2019. Or I guess this is, no, I guess these are months. So this is March of 2019. So what the meaning of this number is in the data is that in March of 2019, property in Beverly Hills, the zip code 90210, is valued at $1,312 per square foot. Okay, so that's the meaning of this number here that's part of our data. Right? So this is a really important number because it's going to give us a baseline for just based on how large the property is, how much would we expect that property in that zip code to sell for, right, for a selling price. So let's suppose that our buyer's house is 3,500 square feet. I don't know that's true for the example that we looked at because it was just a joke video. It wasn't actually an episode of House Hunter. So I'm just going to make up a figure for a relatively large house in Beverly Hills. And so how would we figure out what that house would be worth in that zip code based on this information? Make sure we can see this calculation here. Well, that's just going to be a proportionality calculation, right? If the value is $1,312 per square foot, based on the square footage, we expect the value of this house to be. And to find this number, I just have to multiply the number of square feet, which is 3,500. I'm going to multiply that by the price value per square foot, 1312, according to this Zillow database. And when I compute that, and I'm going to put this into dollars, I'm going to format it as currency. So here would be the estimate that Zillow's data would give us based just on the size of my house, 3,500 square feet, and on the average cost per square foot for a house in this zip code. And so we would expect this house to sell for, knowing nothing else about it, about $4.6 million. To my ears, that sounds about right for sort of a pretty good-sized property in the Beverly Hills zip code. So those are the two things for you to do for the project this week. Figure out how to estimate your buyer's median income, and also bracket the percentiles on it as well. So look up their jobs in this BLS database and figure out roughly what you think they're going to be making on an annual basis before taxes. And then secondly, estimate the value of their house. Don't worry yet about this present and future value business. That we're going to worry about in our final step of the project, because we're going to have to also take inflation and other things into account. But for now, get that estimate for the value of the house, get that estimate for the incomes of your buyers, and you'll be in good shape as far as the project step goes. So with that, let's take our next steps forward into the material of our course. And as I've listed here in the agenda underneath us, we have sort of two sets of topics that I want to talk about in our stream together today. The first one is about probability arithmetic. So this falls for us under Learning Standard number 9. This is the stuff that was in your Newton Alta work about a week ago. So here the question is, how do we compute probabilities of events by combining the probabilities of other events that we happen to know about? And in particular, we're going to be concerned with finding the probability of a union of two events, the union representing the logical OR of two events. So that's mainly what we're going to talk about here. And then also to make a distinction between risk and odds. These are both ways of talking about probabilities, and in particular about how probabilities might differ across two different groups. Relative risks and odds ratios are actually very common ways of talking about the effects of certain treatments or investigating the differences between groups as part of statistical surveys and things like criminal justice and psychology and other social sciences. So this discussion today, I'm hoping those of you who are in a social science major will be able to take into your research methods, your statistics, your data analysis courses in those disciplines where odds ratios and relative risks are a pretty big deal. And then the second set of topics we'll talk about is about sampling. So if I want to understand something about a large population, a big question, I need to cut that problem down to size and pick a small subset called a sample. What are the ways of doing that, and how do we do that in ways that ensure the highest fidelity of sample to population? How do we get the best conclusions and draw the most sound inferences from a small sample? How do we sample in order to make that work? And what are some of the ways in which, if that doesn't happen properly, that those statistics can be misleading? So let's get started with some probability arithmetic for today's live stream. So we'll start with this with the following example. If I have two events, remember, as we discussed in our first live stream, what an event is nothing more than a set of outcomes for a particular experiment. And because it's a set of outcomes, that makes it into a subset of the sample space. The sample space being the set of all possible outcomes. It's like the universe for our probability. And so because events are sets, anything that we could do with sets way back in our first unit of this course, all that set arithmetic, unions, intersections, complements, all that stuff, we can do those things with events as well. And then ask, what is the probability of those compound events that we get by combining different events together? So here's an example that I'm going to use to illustrate what I'm talking about. We draw a card from a standard deck of cards. One thing I don't like about these problems is that they always assume that everybody knows what a standard deck of cards is. So for our purposes, I'm going to just get around that by Well, let me find a quick visual aid that will help us here. List of standard deck of cards. So I'm just going to get a visual here for us so I don't have to draw out this whole sample space, because that feels like not a good time today. Just because there are a lot of cards in a standard deck. Namely, there's 52 of them. So let me just grab quickly here an image of a 52 card standard deck. Here we go. All right, so let's just quickly take a look at this together. So here's my standard deck of cards. There's 52 of them, right? I have 4 different what are called suits. So the clubs, the spades, the hearts, and the diamonds. And for each suit, I have 13 different denominations. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, and King. So all told, I have 13 times 4. That's 52 different cards that make up a standard deck. Let me get a copy of this image so I can put it on our whiteboard here. Standard deck of cards. Grab an image that we can put onto the whiteboard. I'd like to get an image that's easy to work with here. Whoops. None of my technology likes me very much this morning, I'm afraid. So I'm just going to save this on my iPad, and then I'll go back into our whiteboard. And then let me just plop that into my whiteboard. Okay, here we go. All right, so there is my sample space for this problem. And remember, what is the experiment that we're running here? I didn't read it off. Let me go back and read it off here. So the question is that we draw a single card from a standard deck. And so what that means is that my sample space consists of exactly these 52 cards. These are the 52 possible outcomes that we can expect for this probability experiment. So I'm just going to write here S to label that as my sample space. And they want to know, what is the probability that the card that I draw is either a club or a 10? So what that's doing is that that's defining 2 different events for me. It's defining for me the event of drawing a club. I'm going to call that event C. And it's also defining for me a second event, the event of drawing a 10. Let's call that event T. So C for club, T for 10. Let's take a quick moment and just illustrate on this sample space diagram what these 2 events actually look like. So where is my event of drawing a club? Well, that event is exactly the subset of the sample space, which consists of all the cards on this 3rd row. So there is my subset, subset of my sample space, which corresponds to the event C, the event of drawing a club. C. Meanwhile, what about the event of drawing a 10? Where is that event on this sample space diagram? Well, that sample space, or that event, sorry, is going to be the subset that consists of all of the 10 cards. Right? So everything that falls on this column over there, that comprises my event that we're calling T. And so now we're visualizing these 2 events as respective subsets of the sample space. And what we're asking for in this problem is, what is the probability of one or the other of them happening? So the event of drawing a club or a 10. Remember, back when we were talking about logical reasoning and sets, way back in the first phase of our course, the word or corresponded to the set theoretic operation of union. And so what we're trying to do here is we're trying to find the probability of a union of 2 events. And the 2 events are the event of drawing a club, so that's my event C, and the event of drawing a 10, that's my event T. So this is why this is called a probability of a union of 2 events, because my compound event here combines together the situation in which one of my outcomes occurs or the situations in which my other outcome occurs. Now, we could do this a few different ways. We could remember that all 52 of these events in my sample space, all 52 of the outcomes, sorry, are equally probable if it's a fair deck of cards, equally likely. And so we can use what we know about equally likely outcomes to just compute this probability directly. All I would have to do is count the number of outcomes that are in the union of these two sets and divide it by the total number of outcomes in my sample space. The total number of outcomes in my sample space is 52, because there's 52 cards after all. And then I just have to count how many cards there are in the union of my green set and my purple set. That would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, but I don't count this card because I've already counted it, 15, 16. So there's a total of 16 cards that are in the union of my two sets. And so this probability ends up being 16 out of 52 as a fraction. If we wanted to, we could reduce this fraction down to 4 out of 13. We could take 4 out of 13 and we can convert it into a percentage if we want to. Pull out your calculators. 4 out of 13 as a decimal is about 0.308. 0.308. And as a percentage, that would of course be 30.8%. So that would be the really straightforward, very brute force way of doing this problem. We want to be a little bit more sophisticated about this. And we can do that by hearkening back to our work on survey problems. Remember when we talked about survey problems once upon a time? And in survey problems, the main thing that we needed to make sure we were doing was avoiding double counting anything. I don't want to count any of my cards that are part of my events here more than once. When we were doing this the explicit way a moment ago, remember that when it came to the 10 of clubs, that 10 of clubs belongs both to the set C as well as to the set T. And so I don't want to count it twice, both as a member of C and as a member of T. I only want to count it once. And so how we can do that, how we can make sure that that happens, is that we can just go ahead and count the number of outcomes that are in each one of those two sets. So tell me the probability of the set C, tell me the probability of the set T. Those are both going to have the same denominators in their probabilities of 52, and the numerators are going to be the number of cards in each of those events. But if I were just to do that, I would end up with, the following sum. I would end up with two probabilities whose denominators are both 52 and whose numerators are, respectively, the number of cards in the set C. So that's the 13 cards that are clubs, added to the number of cards that are tens, which is 4. Right. But now maybe you're seeing what's happening. If I add the 13 cards from this set together with the 4 cards from that set, there are cards that are getting counted more than once. In particular, there's actually just one card in this example that's getting counted more than once, the 10 of clubs. So if I just want to keep a running narrative of what it is that I'm doing here, I'm adding together all of my clubs, I'm adding together all of my tens, but I'm counting that 10 of clubs more than once, and I need to fix that. And the way I fix that is by subtracting that one card away to take it from being double counted down to being single counted instead. That's the thought process that you use in survey problems to avoid double counting the members of intersections of a Venn diagram, is you had to take away the intersections. Right? And so here I'm going to subtract how many clubs that are also tens. Club tens. Well, there's only one card, which is both a 10 and a club. And so the numerator there is 1. The denominator is still 52. And sure enough, when I remember to account for that double counting, I add these fractions together. Their denominators are all 52, and so the sum remains a denominator of 52. The numerator is 13 plus 4 is 17. minus 1 is 16. Sure enough, that's exactly what we had when we counted it using brute force. So, the takeaway from this example here is that to count a union, to determine the probability of a union of two events, it is not enough to just add together the probabilities. We also need to subtract the probability of the intersection so that we don't double count any outcomes as being part of more than one set. Because that is, after all, the cardinal sin. So we're going to move forward from this probability example to talk about a more applied example of the nature that you're likely to see if you're, again, in a social science major and looking at quantitative studies in the social sciences, as well as some in the physical sciences. I'm thinking of medical trials and things like that. A lot of the ways in which psychologists and social scientists and medical researchers report the effect of a treatment is they report it in terms of relative risks and odds ratios. So I want to take a little while to talk about those terms and figure out how to use relative risks and odd ratios in some sort of concrete scenarios. Sorry, I'm in the wrong. Hold on, let me just real quickly refresh my iPad. Like I say, today, I don't know what it is, but my technology is not cooperating. Here we go. Let me just get this, rein this back in here. All right, I think we're ready to actually do this. So the first bit of terminology that I want to cover together is what is the difference between risk and odds, because these terms are used very specifically in the statistical literature. And so we need to know what exactly is the difference between the two. What is the difference between a risk and odds? Well, if you've ever gambled, I certainly have, not very often, but from time to time, you know that it's very often for the likelihood of winning in a gambling proposition is usually reported in terms of odds rather than in terms of percentages or probabilities. And so the way that odds work is that odds compare the likelihood of something occurring to the likelihood of that thing not occurring, non-occurrences. And if that's a little bit confusing, I kind of like the example that's on this PowerPoint slide here from Newton Alta that explains the difference. So if I roll a single die, a single fair six-sided die, my sample space for that roll is going to be just the numbers from 1 through 6, each with equal likelihood if I have a fair die. There's my sample space. And so if I want to know the odds of rolling a 5, then I'm going to be comparing two numbers from this sample space. I'm going to be comparing my one occurrence, so the one outcome which gives me a positive for this occurrence, so 1. And I'm going to be comparing that one to the other outcomes that are not occurring in that case. So there's one way in which I can come up a winner, and there's 5 ways in which I can not come up a winner. And so the odds in favor of rolling a 5 are 1 in 5. Sometimes reported as odds makers using the word 2, 1 to 5. Right? There's one way in which this thing can happen. There's 5 ways in which this thing cannot happen, and so the odds are 1 to 5. We could also think pessimistically about this and talk about what are the odds against rolling a 5. And for that, we just turn the occurrences and the non-occurrences on their head. We just flip-flop them. So The 5 non-occurrences get stated first, and the 1 occurrence gets stated second. So the odds, we would say, are 5 to 1 against rolling a 5, right? Okay, so this is how we compare odds, is we're dividing up the sample space into the event of my thing happening and the event of my thing not happening. And those two are complementary to one another. One of them is the complement of the other, thinking about set theory again, right? If one of those happens, the other one does not. Occurrences versus non-occurrences. Right? And so odds are comparing the probability of occurrence to the probability of non-occurrence. So how is that different from risk? When we talk about risk, risk is what we've been up to this point speaking of as probability. And the way that a risk is reported is it compares the occurrences, the probability of the thing we're interested in happening, to the entire sample space, the probability of anything at all happening, which is always 100%. So in other words, my numerator for odds and risk are the same. My denominator is different. My denominator for odds removes out the favorable occurrences and gives me just the non-favorable occurrences. Meanwhile, for risk, my favorable occurrence is actually a part of that denominator because the denominator is the entire sample space. So we would say here, so this diagram that we had over here was for odds. The odds of rolling a 5 were 1 in 5 because one way it can happen, 5 ways that it can't happen. If I want to state what the probability or the risk of rolling a 5 in this experiment would be, then I want the same numerator. Remember, I want that 1 to be in my numerator, but my denominator is not going to be the same. My denominator is going to be every outcome in the sample space now. 1, 2, 3, 4, 5, 6. And so the risk of rolling a 5 is going to be 1 out of 6. So there is a difference between risks and odds, just in how they compare the favorable occurrence, the occurrence we're sort of interested in, to the rest of the sample space. For odds, we take away the occurrence itself and compare it to the non-occurrences. For risk, we leave that occurrence in and compare it to the entire sample space. So that's the difference in talking about these two different concepts. And so what we want to do now is think about how do risks and odds get reported in quantitative research, so social science research studies and medical research and those sorts of things. How do those studies deal with reporting of risk? Sorry, let me reset my iPad one more time. Here we go. All right, so this is the example I want us to look at. This is very much like the kind of statistical reporting that would happen in a medical research study. So this is sort of concocted data from a medical research study. And evidently, the goal of this study was to determine whether or not a new flu vaccine was actually effective in helping people not to catch the flu compared to the traditional flu vaccine. So this data here is being reported as one of these two-way contingency tables, one of the most common ways of very transparently reporting the outcomes of a set of two-factor data. Two-way, sometimes just abbreviated two-way table. If you're in one of those social science majors where you're going to take a statistics and data analysis course later on, get used to seeing two-way tables. This is one of the most common ways to report data that comes out of a two-factor study. So, what is the question asking us to look at? Looking at this flu vaccine data, we want to know if I received the new vaccine, so if I were a part of this row right here, then I could ask a couple of different questions, right? I could ask, what are the odds of catching the flu? Or what are the odds of not catching the flu? If I ask those questions, I'm going to be ultimately trying to compare. Let me set the table here a little bit. What I want to do is I want to come up with a way of comparing either the odds or the risk, the probability, of catching the flu for this group of patients that received the new vaccine compared to this group of patients that received a traditional vaccine. Right? Ultimately, whether or not my new vaccine is more effective than the traditional is going to depend on a comparison between those two odds. The odds of me catching the flu if I had the new vaccine versus the odds of me catching the flu if I had the traditional vaccine. So I want to think about dividing up my data here into these two groups. I'm going to color code them blue and orange here. So my blue group, I'm going to call N. This is my group who received the new vaccine. And if I'm working for a pharmaceutical company or a medical research firm or whatever that's developing this new vaccine, then I definitely care about the odds of people who received that vaccine catching the flu will be, but ultimately I need to be able to compare them with what's often in these studies called the control group, the group of patients who received the traditional vaccine. So those are two of the rows of data in my two-way contingency table. And then I also want to think about the two columns in my table, in my two-way table. The column of patients who caught the flu, so let me highlight that one right here. I'm going to call that column C. This is the event that a patient caught the flu. Helps if I spell correctly. And then, of course, everyone who doesn't belong to that column, who caught the flu, will belong to the column that did not catch the flu. And so that is the complement. Call it C complement. Didn't catch the flu. Did not flu. Okay, so I'm just assigning some names to these events that are going to hopefully make it easier to sort of say what it is that we're talking about. I want to know, whoops, that wasn't the technology, that was a slip of my finger, sorry. I want to be able to say, in both odds language and also risk language, how likely are the patients in these groups to have caught the flu or not? Right? So the question here is, what is the odds ratio or what is the relative risk of not catching the flu for those who receive the new vaccine? So I need to know a couple things. Let's start with risk, because this is language that we're more comfortable with right now because we're used to talking about probabilities. I want to know, first of all, what is the probability given that I received the new vaccine that I did not catch the flu? That I didn't catch the flu. You can kind of think of this as like the immunity rate or something, right? How effective was this vaccine in preventing the flu in the people that received this new vaccine? So that's the first thing I want to know. And for this is a conditional probability. So we talked about conditional probability last week, right? Because of the word given, this is kind of the watchword here, right? We know that this is a probability whose sample space is not the entire sample space of everybody in the study, but is only the sample space of people who received the new vaccine. So it's a conditional probability that looks only at the row that has the new vaccine patients in it. So this is conditioned on N. I'm looking only, so let me take this opportunity to just completely obscure the rest of this table, because in computing this probability, that part's not going to matter. Right? I want the probability that I did not catch the flu, so that's C complement here. So given that I received the new vaccine, what's the probability that I didn't catch the flu? So to figure that out, as with any probability, I'm going to take the number of occurrences, 375, and divide it by, because we're doing a risk, we're dividing it by the total. 375 divided by 390. So 375 divided by 390. And of course, I can't do that arithmetic off the top of my head, so I'll pull out a calculator. 375 over 390. That gives me 0.9615. I'll round it to just those 4 decimal places here. 0.9615. Or if you like, that's 96.15%. So if I received the new vaccine, there's a 96.15% chance that I didn't catch the flu. Right? That's pretty close to 100, our brains say, right? So it would seem that this new vaccine was pretty effective in preventing its recipients from contracting the flu. But how effective is effective enough for me as the pharmaceutical company research and development director to be able to say that this vaccine is actually more effective compared to the traditional vaccine at preventing the flu? That's why we don't just want the risk, we want the relative risk. I want to be able to compare this probability to the probability of catching the flu given that I had received the traditional vaccine. So we have to compare the number that we just got to the same calculation, just instead of given the new vaccine, given the traditional vaccine. So now we need to redo this probability. What is the probability given that I received the traditional vaccine that I didn't catch the flu? I didn't catch the flu. Right? So I have to know that number as well. Otherwise, I don't have a point of reference to claim whether or not my new vaccine is more or less effective at preventing the flu compared to the traditional treatment. So here again, we need another conditional probability, except now I'm conditioning my probability on the sample space of the patients in the trial who received the traditional vaccine. So now my new vaccine patients are irrelevant, and I just care about my traditional vaccine patients. So my probability is conditional on on T, on having received the traditional vaccine, right? I want to know what's the probability that I did not catch the flu. So, once again, because it's a probability, a risk, I'm going to compare the number of occurrences to the total number of all occurrences. And so the relative ratio that I want here is 225. So that's the number of traditional vaccine recipients who contracted the flu, who did not contract the flu, 225. And then I'm going to divide that by the total number of patients who received the traditional vaccine, and that number here is 280. 225 out of 280. So once again, pull out a calculator. 225 divided by 280. I get 8.8036. Again, I'm just kind of rounding a little bit. 8036. Or as a percentage, 80.36%. So what we can say then is that among the patients who received the traditional vaccine, about 80% of them were immunized from the flu, did not catch the flu. Among those patients who received the new vaccine, 96% of them did not contract the flu. Right? And so on its face, it would look like the new vaccine is more effective at preventing the flu compared to the traditional vaccine. 96% of new vaccine recipients did not get the flu. 80% of traditional recipients did not get the flu. And the relative risk assigns a number to that comparison. And both for relative risks as well as for odds ratios, that number, that comparison, is achieved by dividing. So the relative risk I'm going to get by dividing these two probabilities one by another. Divide, divide, divide. Any of these divisions is going to give me the same answer at the end of the day. And so the relative risk, I'm just going to pull out a calculator one more time, and I'm going to divide 0.9615 divided by 0.8036. 9615 divided by 0.8036. And when I do that, I get a number, 1.196. I'm just going to do it to 4 decimal places. We call that number the relative risk. And so these are the kinds of numbers that you'll see in a medical research study. of this data. The relative risk between these two groups is 1.196. And the way that we can contextualize this, so I'm going to write this in words here to finish this up, is that we can say that patients receiving the new vaccine so they had immunity rates that were 1.196 times as large as the people in the referent group. Right? So patients receiving the new vaccine were, and how I would say this is I would chop off this 1 at the beginning and turn the 0.196 into a percentage. 19.6% more likely to not catch the flu compared to those who received the traditional vaccine. So that's the way to get a relative risk out of a problem like this. Just find each of the probabilities, and each of those probabilities is going to be conditional on the group that you belong to. In this particular contingency table, those groups were the groups listed in the rows. I think that's pretty common in social science studies as well. Right? So on each row, get the conditional probability that you're interested in, and the relative risk will be the ratio of those two conditional probabilities. And because it's a ratio, we always contextualize it as how many times as much is one group compared to the other. How many times as high is the rate or the risk at which the new vaccine patients didn't catch the flu compared to the rate at which the traditional vaccine recipients did not catch the flu. So there's relative risk. What about odds ratios? There are probably good statistical reasons why one would favor odds ratios over relative risks. I don't actually know what those are. So because these are both ways that these comparisons get reported in studies, we'll cover both of them. And then the choice of which one to use in a given study, that's really more of a kind of question that you would answer in a more advanced sort of research methods class. And we're going to just be satisfied in our introductory math course here with knowing what these things mean and how to actually compute them. So for odds, we're going to do the same process as we did before, except that instead of dividing probabilities, I'm going to divide odds instead. So let me just write that out first. So I'm going to be dividing the odds of no flu in the new vaccine group divided by the odds of no flu in the traditional group. Right? And when I divide those two things, I'm going to get a ratio that we call, unsurprisingly, the odds ratio. And so the only difference here is in how we compute each of those two figures. Let's think about how to compute the odds among the new vaccine patients of not getting the flu. Again, this is a conditional odds. We don't care about the traditional vaccine recipients for the moment. We just care about those who receive the new vaccine. But remember, I'm going to go back a slide if it doesn't break my iPad here. When we compute odds, we're comparing not occurrences to the entire sample, but we're comparing occurrences to non-occurrences. And so, if I want... Uh-oh. Now I got to reset my iPad again. I knew I was tempting fate by trying to switch from one slide to another. So to get these odds, instead of dividing the 375 who didn't catch the flu, instead of dividing that number by 390, as we did when we were finding the relative risk, instead now I want to divide that 375 number of occurrences by the number of non-occurrences of not catching the flu. In other words, the number of occurrences of catching the flu. 375 divided by 15. So that's how I'm going to get my numerator up here. 375 divided by 15. Because now that becomes an odds rather than a probability or a risk. Same thing for my denominator. If I look at just the traditional vaccine group now, try and get my table back. Here we go. If I look just at the traditional vaccine group, and I ask, what is my odds of no flu among this group, I'm again going to divide the 225, same numerator, remember, not by the total number of traditional vaccine recipients, but by the total who caught the flu, 225 over 55. So for my odds ratio, that's what I'm going to end up dividing, right? If I decided that I wanted to simplify these odds, I could, right? 375 over 15, I could reduce that as a fraction. What is 375 over 15? It's actually 25 to 1. So if I was in the new vaccine group, the odds of me not contracting the flu, the odds in favor of my not contracting the flu, were 25 to 1. Another way to say that is the odds against my not contracting the flu. In other words, the odds in favor of my getting the flu were 1 in 25. Okay, and then for the other group, 225 over 55, if I look at that fraction, that would be 45 to 11. Kind of a nasty, reduce that fraction. 45 to 11. Whatever. It's a weird way to report odds, but it's a very common way to report odds. But if I'm looking for the odds ratio, I would be dividing those fractions one by another. So if I'm going to divide those fractions, probably easiest if I just make them into numbers instead of into sort of sentences. This is the number 25, and this is the number 4.091. And so then I would divide one of those by the other, right? 25 divided by 4.091. Get out my calculator. And I would get 6.11 approximately. Right? And so my odds ratio, 6.111. Again, because it's a ratio, we still have to interpret it in terms of a multiplicative comparison. This time, a multiplicative comparison between two sets of odds. So, how I would contextualize this is I would say the patients receiving the new vaccine had 6 times the odds of not contracting the flu compared to the patients who received the traditional treatment. Right. So again, the ratio part of relative risks and odds ratios is the same. The only difference is in how we compute an odds versus how we compute a risk or a probability, right? And as you can see from this example, relative risks and odds ratios can give you very different numbers. And that may be one reason, again, to prefer one of these types of reportings compared to another. Whoops, let me reset my iPad yet one more time because I just bumped it and I lost it. Here we go. So the two numbers are very different. And I guess the moral of that story, particularly if you're an aspiring social scientist, like a psychologist or somebody in criminal justice, most important thing about these is to be aware of which one is being used in which context, because how you interpret these numbers is very different depending on whether these numbers are telling you about odds versus whether they're telling you about a risk or a probability. I'm going to take just a quick 30-second break here, and then we're going to go forward and talk for a few minutes about sampling and ways in which sampling and other sources of bias can mislead in the computation of statistics. So just about 30 seconds, and then we'll come back and do that last step of today's live stream. So I just found out that for the last 20 or 30 minutes or so, my mic has been muted. Not the first time that I've done that. So let's go back a couple of slides to where we were talking about sampling methods, and we'll give the 40,000-foot flyover of this just to wrap things up for today. So, actually, is this the best way to do it? So we talked about different types of sampling and what each of these types mean and how to identify what type of sampling is happening in a given problem. From there, we moved on to talk about ways in which statistics can be used to mislead. And there's a variety of different ways. The most interesting one that I wanted to focus on in this problem was just how we can use a visual aid to either illuminate or to mislead. So this bar chart was a very misleading way to represent the difference between the number of people who said that they prefer Pepsi versus the number of people who said that they prefer Coke. I'm sort of making up brand A and brand B here. So if I'm Pepsi, I might show this bar chart and say, look how many more people support us compared to support Coke. The problem is that the vertical axis on this chart is missing a scale and it's missing a 0 point. And so without that 0 point and that scale, I lose the ability to make a visual comparison of the relative sizes of these bars to one another. In particular, if I were to fix this chart, the way I would do it is by taking the scale which is present between the 150 and 120, that scale of 30, and just extending that scale down until we get down to 0. And once my 0 point is included, now I have a bar chart that can show me both the absolute difference in support between these two brands. 30 more people prefer Pepsi compared to Coke. But it also now accurately visually conveys the relative difference, that there's 25% more support for Pepsi here than there is for Coke. And there are studies in developmental psychology that show that when children and babies are learning numbers and quantities for the first time, the very first kinds of number and quantity comparisons that we learn to make instinctively as children is comparisons about the relative sizes of quantities, percent changes, not amount changes. And for that reason, the first instinct that we have when looking at a visual is to assess the relative sizes of the visual elements that are in that chart, not the absolute differences like the 30 people difference, but the 25% bigger difference that's now accurately portrayed on this chart. So make sure your charts include zeros and that they include scales, so that we have visual ways of performing both an absolute comparison, but also an accurate relative comparison between the sizes of two things. That's where we're going to wrap up today's live stream. So remember, if you're in my class this semester, your project steps for this week are to come up with, research some statistics on what the buyers in your House Hunters episode might reasonably be making based on their income and geography. And then also an estimate on the value of the house that they purchased based on its location and its square footage. And again, you can find links to the Bureau of Labor Statistics site that I used for that research, as well as the Zillow site for home values by zip code. You can find those links on my blog. I'll post a link to that on our Slack site as well. So I hope you have a good week. We're going to come back for one more live stream next week where we'll talk about the statistics of the normal distribution as a way to wrap up our semester.